Well, in nuclear physics, our today's discussion will be from nuclear fission. Nuclear fission is a phenomenon in which a heavy nucleus is disintegrated by slow neutrons, that is having energy 1.2 million electron volts. As a result, there is formation of a heavy nucleus, that is, we will find barium, that is uranium-236, and finally it splits into two light nuclei, that is barium and krypton. So nuclear fission is a phenomena in which a heavy nucleus is disintegrated by slow neutrons, giving rise to two light nuclei along with three neutrons and 200 MeV of energy per atom. Out of these three neutrons, we find that two neutrons are used for chain reaction and one neutron known as the thermal neutron that give rise to the thermal variations in the surrounding medium. And the light nuclei, they are called the nuclear fragments, and basically they are transmitting the visible radiations, and these visible radiations have frequency of about 10 to the power 15 hertz or 10 to the power minus 7 meter wavelength. Moreover, during nuclear fission, two neutrons out of three are used for chain reaction. In the first generation, when we get three neutrons, two neutrons give rise to chain reaction and one neutron is the thermal variation. But when the next generation starts, we will get total number of neutrons as, that is, 4 for chain reaction and 2 for thermal variations. The multiplication of neutrons will be in geometric sequence, that is, the ratio of chain reaction neutrons to the thermal neutrons will remain 2:1. Up to the time this type of ratio will be maintained, we will find that reproduction factor K will be greater than 1 and chain reaction will continue, but the moment K will be less than 1, the chain reaction will stop. These are the basic fundamentals we have to use in the nuclear fission. Now we discuss more elaborately about the nuclear fission. In order to start the nuclear fission, first of all, we will remember that there are three natural isotopes of uranium. One of them is 92 uranium-238, other is 92 uranium-235, and the third one is 92 uranium-234. 92 uranium-234 is found in traces, that is very small amount. However, the availability of 92 uranium-235 is about 0.7%, and in abundance we have 92 uranium-238. Now, these are the three natural isotopes. But for fission, we require 92 uranium-235, that is a natural fissionable material, and other is a synthetic fissionable material, that is 92 or 94 plutonium-239. Now, first of all, we will remember that 92 uranium-238 is bombarded by a neutron, and that transforms into synthetic uranium. Then synthetic uranium give rise to, that is neptunium, or it give rise to a beta particle, that is 92 uranium-239. When it give rise to beta particle, a higher atomic element is formed, that is 93 neptunium-239. This neptunium-239 give rise to again a beta particle and transforms into 94 plutonium-239. The plutonium-239 is a synthetic fissionable material, and this synthetic fissionable material give rise to an alpha particle. As a result, there is formation of 92 uranium-235. Now, this 92 uranium-235 is disintegrated by slow neutron of energy 1.2 MeV. There will be formation of 92 uranium-236, which splits up into 56 barium-138 and 36 krypton-95. These are called the nuclear fragments, and along with this, there is formation of three neutrons and 200 million electron volts of energy per atom. The nuclear fragments have tendency to generate visible radiations having frequency about 10 to the power 15 hertz and the wavelength about 10 to the power minus 7 meters. So now we come to the main concept. This phenomenon of nuclear fission was first discovered by scientists, that is Otto Hahn and F. Strassmann. The process of splitting up a heavier nucleus by bombardment of neutron into two almost equal weight nuclei is known as nuclear fission. And in this process, an account of the mass defect, huge energy is liberated. Very more elaborately, uranium-235 is a heavy nucleus. It is bombarded by slow neutrons, and then there is formation of uranium-236, which splits up into two light nuclei like barium and krypton with 3 neutrons and 200 MeV of energy per atom. Natural uranium is obtained in the following proportion. So this proportion I have already explained you that 92 uranium-234 that is existing in traces, 92 uranium-235 it is a natural fissionable element and its existence is about 0.7%. 92 uranium-238 that is abundantly existing, its availability is about 99.3%. This I have already explained. Now uranium-238 is not basically used for fission because fission is possible only by the neutrons of energy approximately 1 to 1.2 MeV, and uranium-238 is more stable as compared to uranium-235. So this uranium-235 is otherwise bombarded by slightly a fast neutron and then it transforms into 92 uranium-239. This uranium-239 is further disintegrating according to its life period and we get neptunium, that is uranium-239. This uranium-239 converts to neptunium. Neptunium is converted into 94 plutonium-239 which finally converts to 92 uranium-235 by giving out alpha particles. So it is quite easy to explain the phenomena, but it takes a lot of time for the transformation of uranium-238 into uranium-235. So next is the fission of uranium-235 is possible by the slow neutrons. When we use this term slow neutron, energy is nearly 1 to 1.2 million electron volts or even by thermal neutrons of energy 0.025 eV. So better is to understand only slow neutrons and energies are variable under certain limits. Now fission reaction that is indicated in two stages. First of all, 92 uranium-235 which is recovered from 238 is bombarded by a slow neutron and then it transforms into 92 uranium-236 that is unstable uranium and this uranium-236 transforms into two light nuclei that is barium and krypton along with 3 neutrons. The whole reaction is indicated as follows: 92 uranium-236 when it splits it gives rise to 56 barium-141, 36 krypton 95, then 3 neutrons and about 200 MeV energy per atom. The point to understand is that 3 neutrons move in different directions because their momentums are different. However, out of these 3 neutrons, 2 neutrons are used for chain reaction and 1 neutron gives rise to the thermal variations. In case of barium and krypton, it is not necessary that we get 141 and 92 as the mass numbers. Sometimes we get 56 barium-138 and 36 krypton 95. But 3 neutrons are imminent. They are to be formed. Moreover, the ratio of the chain reaction neutron to the thermal neutron will always remain 2:1. In the first generation, there will be 2 chain reaction neutrons and 1 thermal neutron. When we come towards the second generation, there will be 4 chain reaction neutrons and 2 thermal neutrons. In the third case, it will be 8 chain reaction neutrons and 4 thermal neutrons. That is the multiplication of neutrons go on in geometric sequence. During 92 uranium-235 fission, we don't get only isotopes barium and krypton. We can also get other pairs also like strontium and xenon. As it is clear from the equation, uranium-235, it is bombarded by 0 and 1. There is formation of unstable uranium and it finally transforms into 38 strontium-95, 54 xenon 139 with 2 neutrons and 200 million electron volts of energy per atom. Well, you will remember that xenon is inert gas, helium, neon, argon, krypton, xenon, and strontium. This is also one of the fragments. We find that 2 neutrons are generated in this process, and by fission of uranium-235, we get approximately 200 MeV of energy per atom. By fission of uranium-235, on an average 2.5 neutrons are liberated. This is the average number of neutrons generated during fission. We will further remember that uranium-238 transforms to 235 in one of the part of the reactor. We can remember that in nuclear reactor there are 3 components. One of the component is fuel unit, the other is moderator, and the third one will be control rods. So in the fuel unit, 92 uranium-238 is bombarded by neutron, and in various stages it transforms into 92 uranium-235. Then we get neutrons from a source, that is 4 beryllium-9, and the neutrons are first of all passed into the moderator where they are slowed down and their energy is brought to 1 to 1.2 million electron volts. Then those slow neutrons are bombarded on 92 uranium-235, which we recover in the fuel unit. Moderator is generally made up of heavy water, or it is made up of some other materials like beryllium also. And then there is the third part, that is the control rod. Whatever neutrons are generated in the process, we find that excess number of neutrons, they are absorbed by the control rods, that is made up of cadmium. Neutrons emitted from the nuclear fission have energy equal to 2 million electron volt. These fast neutrons can escape from reaction so as to proceed the chain reaction. They are to be slowed down. Well, now the nuclear fission means disintegration of a heavy nucleus by the slow neutrons. Unstable radioactive nuclei. One is uranium-238, other is uranium-235. We recover 235 from 238. And stable lead. These are the 2 nuclei shown as stable lead. And energy radiated in the process about 1 million electron volt to 5 million electron volt. Otto Hahn explains the phenomena. And uranium-235 nucleus is disintegrated. So in the animation it is shown 92 uranium-235. It is bombarded by a slow neutron. There is formation of a compound nucleus. This compound nucleus is in the form of 92 uranium-236. This will split into 2 light nuclei. One is barium, other is krypton. So in the whole animation, neutron is bombarding uranium-235, which is recovered from 92 uranium-238. Due to capture of neutron, a compound nucleus, uranium-236, is produced. That finally splits up into 2 lighter nuclei like barium and krypton with atomic number 36 and 56, mass number 92 and 141. It is not necessary that the mass numbers will be 141 or 92. It can also be krypton 95 and barium, that is 138. So 3 neutrons are always produced. This is what's shown in this particular animation.